Hello students, in this video we'll find the solution to the heat equation on the entire real line. So the problem we're going to consider is the following. We're going to consider the partial differential equation ut is equal to uxx. That's the heat equation for a function u of x and t with the initial condition that u of x and 0 is f of x. And I'm going to assume this function f of x is sufficiently smooth for this procedure, right? And so what's the domain of the PDE? The domain of the PDE is my x variable, my spatial variables between negative infinity and positive infinity, and my variable t is greater than or equal to 0. So that's the domain for this equation over here. So in other words, what we have is we're going to look at the real axis, and here's the t-axis, right? And then I have an initial distribution of heat along the real line. So there's a distribution of heat, initial distribution f of x along the real line. And I want to figure out how the heat is changing with every instant of time. So how's the heat changing at time 1, for example? So that's the situation we have over here. And what we're going to do is we're going to Fourier transform one of the variables here. I'm going to Fourier transform the x variable. So the methodology of the proof is we're going to Fourier transform. So let's take the Fourier transform of the function u of xt in the x variable. So I'm going to Fourier transform the x variable only leave t as itself, right? And so what's going to happen if we do this? Well, for example, and so what we're going to get is we're going to take the Fourier transform on both sides. And so the left-hand side is going to be what? Is going to be partial with respect to t of u hat of xc t. So I've changed the x to xc. And of course, here our function really looks like what? Our function is really a function. So this u over here is really u of x and t. It's just real variables. That's what our u is, okay? Great, and this is going to be equal to what? This is going to be equal to the Fourier transform of two derivatives. Now remember the rule for Fourier transform of a derivative. The rule for Fourier transform of a derivative is that if I take the Fourier transform of an x derivative of a function, what this is going to be negative 2 pi I xc times f hat of xc, right? And so if I do two derivatives, this becomes a what? This becomes, that quantity will be squared. So if I did two derivatives, this quantity over here would be squared, and this would turn into a what? This would turn into a negative 4 pi squared xc squared f hat of xc, okay? So what we're going to have over here on the right-hand side of the equation is exactly what? Is exactly negative 4 pi squared xc squared u hat of xc t. And what the Fourier transform has done is the Fourier transform has taken this PDE and turned it into an ODE, right? So this is an ODE in the t variable. Okay? And so what does it really look like? This is nothing more than the following ODE. So if we think of this just from an abstract perspective, this is really just asking the question, can I find a function g such that g prime is equal to this number over here, negative 4 pi xc squared times g. That's an easy ODE to solve, right? That just says that g of t would be e to the what? E to the negative 4 pi xc squared t times some constant c. Now, when we're integrating this with respect to t, I have xc variables to worry about as well, so that's the constant will depend on xc for us, right? So the solution of this is going to be therefore, thus, u hat of xc t by solving this ODE is just what? It's just a constant c which depends on xc. And then what? And then e to the negative 4 pi squared xc squared t. Beautiful. Okay, and how do we find out what this c of xc is, that constant? Well, I can take the initial condition and Fourier transform it. So if we Fourier transform the initial condition over here, I know that u hat of xc 0 is equal to f hat of xc, okay? And so when I plug in t equals 0 in this formula, this is going to turn into a 1, so that c of xc has to be f hat of xc. So this is going to give us that u hat of xc and t is f hat of xc e to negative 4 pi squared xc squared t. Beautiful. Now remember, I have a product of two Fourier transforms. This is a Fourier transform and this is a Fourier transform. And so when I do the inverse Fourier transform of this to get back to my function u of x and t, what I'm going to need to do is I'm going to have to convolve the resulting functions, okay? So it's easy to inverse Fourier transform f hat, it's just going to be f itself, okay? This thing over here is a Gaussian function, and so we have to recall the rule. So what rule do we have? So recall that e to the negative pi squared, e to the negative pi, excuse me, e to the negative pi, not squared, e to the negative pi x squared transforms to e to the negative pi xc squared. This Gaussian function's its own Fourier transform, right? So we're going to use this rule. So what happens if I scale this rule? So now the question becomes is, how do I figure out what this thing is getting inverse Fourier transform to? So now we'd like to say, well, if we have an e to the negative 4 pi squared xc squared t, this is really the same thing as what? This is really the same thing as e to the negative, what's my dilation factor over here? It's going to be a negative 4 pi t, okay? And then we'll have a what? And then we'll have a pi xc squared. So I'm really dilating my function by the square root of this thing. So now what we're going to do is one final step over here. We're going to write this as e to the negative pi and then xc times the square root of 4 pi t quantity squared over here. Okay, so that's my dilation parameter. And so now what do I know? The dilation rule says that this thing will inverse transform to what now? So we're going to use this representation. So now, hence, my u of x t is going to be what? My u of x and t is going to be a function that depends on t. I'm going to call that function phi sub t convolution f of x. Okay, and where phi t is what? Where phi t of x is going to be the inverse Fourier transform of this thing over here. It's the inverse Fourier transform of e to the negative pi and then xc times the square root of 4 pi t quantity squared. Okay, excellent. So what is this going to give us? This is going to give us exactly what? By the dilation rule for the Fourier transform, this is going to be 1 over the square root of 4 pi t e to the negative x squared over what? Over, let's do this carefully over here. So what's my delta over here? So my delta is this thing over here. So I'm going to have a 1 over delta, right? So my delta is this thing. And then e to the negative, let's be very, very slow about this to make sure we're getting completely correct. So here my delta is this parameter over here. And then I'm going to have a what? A negative pi, and then what? And then I have to do x over delta. So I have x over delta, where this is delta quantity squared, right? And so this is going to be a 1 over square root of 4 pi t, and then e to the negative pi, and then x squared over 4 pi t with a square root. Delta squared is going to be 4 pi t, like that. Okay. Good. So the pi is going to cancel out, and we get this exactly that this is going to be 1 over 4 pi t e to the negative x squared over 4t. Good. So that's what our delta of t is. Excellent. Okay. And so now we can write this, we can write down our solution over here. This is going to be what? So this solution is going to be, this 1 over 4 pi t can come outside. The integral over r of f of y, and then e to the negative what? E to the negative y minus x quantity squared over a 4t dy. And so this is my heat kernel representation. This function over here, this phi of x and t is called the heat kernel. And therefore we can represent the solution of our PDE as this convolution. So this convolution structure over here is the solution of the heat equation on the entire row line with initial data that's sufficiently well behaved. And we can see we'll generate lots of different properties of the solution from the heat equation from this representation. Thank you very much.